All right, how's it going? Are you guys ready to start chapter 15? Yay! Gravitation! Oh my goodness, videos are weird and I don't like that I can't see your faces, but we're gonna go for it. So just pretend you can see me and it'll be fine. We got this. So chapter 15 talks about gravitation, and I know we've talked about gravity before. We've talked Fg is mg, the force of gravity goes down, all that good stuff. However, what if we're not talking about just an object and the earth? What if we're talking about the earth and the sun, or the moon and the earth? We have this other equation for gravity. Newton came up with this. Newton's universal law of gravitation. He said that the force of gravity is proportional to the product of the masses and inversely proportional to 1 over the distance squared. So we have Fg is g m1 m2 over r squared. Should make sense. If the masses are bigger, the force of gravity is going to be bigger. And if they're further apart, the force of gravity is going to be smaller. R, all right, is the center to center distance between the objects. Center to center distance. This is important because a lot of times they're not going to give you the center to center distance. Sometimes they give you the altitude, which would be the distance above the surface. So if we look over here at this picture, the center to center distance is from the center of the earth to the center of the moon. This whole center to center distance. But if I tell you the altitude, then that means I'm telling you the distance above the surface of the earth. This is the altitude. So if I want the total center to center distance and I'm given the altitude, all you have to do is add the radius of the planet. So that would be the radius of Earth, whatever planet we're talking about. So to figure out the force of gravity, you want to multiply the masses, divide by the center to center distance squared. All right, but wait a minute. I got this weird letter in here, G. G is the gravitation constant. It is equal to 6.67 times 10 to the negative 11th. Where in the world did that come up with? We actually have this guy, Henry Cavendish, measured by Henry Cavendish. Cavendish. That's not a C. There we go. Cavendis. Yay! Cool. He did this experiment, and the experiment's in one of the last pages of your notes. Actually, let's just do that now. Let's go to it. Scroll to the back. Woo! Where is he? Here we go. This is the Cavendish experiment. He did it in 1798, and what he did is he created a setup where he hung a fiber from a ceiling. So up here, this is my ceiling. He hung a fiber from it. So this is my line hanging down it. And we're going to place a rod on either, or at the end of that fiber. On either end of the rod, we're going to place 2 little masses. So 2 small masses are placed at the end of the light rod. The force required to rotate the fiber from its untwisted position is measured. So he could figure out how much force is required for this to actually move. Then what we're going to do is we're going to bring 2 large masses next to these little masses. And we were just told, or I just told you, or he knew, that the force of gravity would bring these together. So what happens is, as he brought these 2 large masses, it twisted some angle theta. If you watch a YouTube video, they actually show these live. You can go check it out. People have set this up, and you can actually see this will literally move strictly because of the force of gravity. So what happens is, if he knows the force required to twist it, so he knows the force of the twist, he knows that that is gravity, he knows the distance between them, and he knows both of the masses. The only variable left is this g. So he could calculate what constant is required in order to make this law hold true. And he came up with 6.67 times 10 to the negative 11th. Pretty neat experiment in my opinion. Again, go watch a YouTube video. Watch YouTube. If we were in class, I would show you and you would have to. But it's pretty cool. So I would highly recommend you go do that. Just, YouTube Henry Cavendish and you can see it. All right, awesome. Back to the beginning. Whoa. I don't know why that's doing that. Well, this is embarrassing. We're just going to keep going with it. This page got all messed up, but it's fine because I have my notes out next to me. You can see on your notes that what that problem says is calculate the acceleration due to gravity on any mass m near the surface of the Earth. We are told that the mass of the Earth is 5.98 times 10 to the 24th, and you also need to know that the radius of the Earth is 6.371 times 10 to the 6th meters. We want to find the acceleration due to gravity of any mass. So you guys obviously know what this is. It's 9.8. We've done this before, but let's show where 9.8 actually comes from. If we start with our law of gravity, Fg equals g, m1, m2, but I'm going to be more specific because I know the two objects. It's the mass of the Earth and the mass of the object, divided by the distance squared. Well, if we're at the surface of the Earth, the distance is the radius of the Earth. We also know that the force of gravity is mg. Now we've got two equations for the force of gravity. We can set them equal to each other. No way. Crazy. G, M-E, M over R-E squared is going to equal mg. Now this mass, when we did this back and forces, this was the mass of the object. This is the mass of the object. That's important because that tells you which mass to cancel. The mass of the object is the mass we used when we were trying to find the force of gravity on Earth. So mg is the mass of the pen or the mass of, you, whatever object you're dealing with. So the mass that's canceled is the smaller mass, leaving the mass of the object in the center. So this mass is the mass of object in the center. So if we're talking about the sun and the Earth, then that would be the mass of the sun. If we're talking about, Jupiter and its moons, that would be the mass of Jupiter. Whatever that larger mass is. So if we keep going, this tells us that little g, the acceleration due to gravity, is going to equal capital G, which is our constant, keep little g and big G separate, times the mass of the Earth divided by the radius of the Earth squared. This is good to know. This will always be true. Again, the M and the R will change, but you can pretty much always do this little trick and say, okay, I know Fg is two things, let's set them equal to each other and the mass cancels. Now I can solve for the acceleration due to gravity. So if I actually do it and we plug it in, we've got 6.67 times 10 to the negative 11th times the mass of the Earth, 5.98 times 10 to the 24th, divided by 6.371 times 10 to the 6th squared. Oh my goodness, get your calculator out. You get 9.82 meters per second squared. How cool! We just proved it. Ah, crazy. So another question I get all year is how in the world do you calculate the mass of the Earth? This is how you would calculate the mass of the Earth. Little g, the acceleration due to gravity, you can calculate. You can do an experiment. You can drop an object and measure the distance and time it takes to fall. Capital G was just talked about. That's our constant calculated by Henry Cavendish. And the radius of the Earth was actually calculated by this Greek astronomer Eratosthenes. This is another cool thing to YouTube. He made a experiment where he actually looked at the shadows in two separate places on the Earth, and they were different. At one place in the Earth, there was no shadow. At another place on the Earth, there was a shadow. From that, he concluded that the Earth must be round. And because of that, he could actually calculate what the radius of the Earth was. So if we know acceleration due to gravity, we know the gravitational constant, and we know the radius of the Earth, you can figure out the mass of the Earth. What craziness, I know. All right, flip, next page. So as objects are going in circles, so we have the moon going around the Earth, we could have a satellite going around the Earth, we could have the Earth going around the sun, we can use this gravitation formula to figure out the speed that they must be traveling. In order to do that, we know that the gravitational force has to be the centripetal force. So G, mass of the one planet, so we can have Earth, times the mass of the satellite, divided by the center to center distance squared is going to equal the centripetal force, well, goodness gracious, remember that, mv squared over r. Now again, you need to know what mass we have over here. This is going to be the mass of the satellite. That's the mass of the object that's going in the circle. When we did circular motion, it was always, the car was going around the bend. So the car was moving in the circle. When we had the tennis ball on the string, the tennis ball was the one moving in the circle. So the circular motion, centripetal motion equation is the mass of the object moving, leaving the mass of the object being orbited. So what we can do, cancel that mass, cancel one of the r's, and what we're left with is that the speed is going to equal the square root of g m over r. I'm going to write it as a capital M. I suggest you do that too. That's to remind you that's the mass of the object being orbited. It's the larger of the two masses, whatever mass is in the center. So we have numbers here, so we can actually plug it in. If we want to figure out the velocity, we know that it's at a height of 645 kilometers. That's the altitude. That's this little h here. Let's get a new color. This right here is 645 kilometers. But we want the total center to center distance. So this r is going to equal the radius of the Earth plus the height. Well, easy enough. Just be careful of units. Kilometers make meters. And then we can actually plug it in. Here, we'll box this because this is an equation. I would learn that one. Now we can plug in our numbers. What we end up with is the square root of g, 6.67 times 10 to the negative 11th times the mass of the Earth, 5.98 times 10 to the 24th. Just got it in there. Divided by the total distance, 7016000. Calculator time, 7,539.95 meters per second is what I got. Yay! Oh man, I missed. Let's try again. Very necessary. Much better. Cool. So we got a lot of room on this page. Let's talk about one more thing. I should have been timing this. I have absolutely no idea how long this video is. So, torque, and satellites. Remember what torque equals? Torque is R cross F. It's really weird not having you guys answer that. I have to answer all my own questions. I'm going to sound like a crazy person. That probably made me sound crazy just by saying that. Well, torque, R cross F, is RF sine theta. So RF sine, what in the world is the angle? Well, it's actually 180 degrees. It's the angle between the radius vector and the force vector. So if we look back up at this picture for us, the radius vector starts at the center and goes out. There's my R. But where's my F? The force of gravity is therefore inwards. So the angle between those two ends up being 180 degrees. And what's sine of 180? 0. I really want to do an exclamation point after that, but it's not 0 factorial, it's just 0. So we're going to not do that. So since the torque is 0, we also know torque is dl dt. That means that the change in angular momentum has to also be 0. Hey, this looks familiar. We've done this before. That means that the initial angular momentum equals the final angular momentum, and angular momentum is conserved as we have our satellites going around in our circle. Yay! Conserved. Woo! All right, we'll do one more page. So here we have 3 satellites. This is the equation we derived on the page before. We've got 3 satellites. What we're going to do is we're going to talk about how a satellite can possibly change orbit. In order for a satellite to be in orbit, it has to be going a certain speed. You can calculate that speed, we just did. But what if we want to change the orbit? That means we have to change the speed. Looking at this equation, if you have a smaller radius, you're going to have a quicker speed, right? So if I have R1, my inner guy, versus R2 versus R3, the slowest moving satellite is going to be R3, the quickest moving satellite is going to be R1. So how in the world do I change my orbit? So what if I want to go from orbit 2 down to orbit 1? Well, in order to get it to actually move into that closer satellite, first you're going to have to slow the satellite down. So first, slow satellite down. If we first slow the satellite down, we can get it to move closer to the Earth. However, it will not be stable there. You will not have a stable orbit. So what you'll have to do is then give it some more speed. So now, speed it up to whatever speed you need. We know is that v equals the square root of g mass of the Earth over r. If you don't give it that extra speed, that satellite will not be stable. It will fall to the Earth. It will not be able to be in orbit at that location unless you give it the proper speed. Awesome. So then, what if we want to go the other way? What if we're going from 2 to 3? Go from 2 to 3. Well, it's going to be the opposite. First, you're going to have to speed the satellite up. Speed satellite up. satellite up in order to get it out of that orbit to the further orbit. However, again, it won't be stable there. In order to speed it up, you're going to then have to slow it, or in order to change the orbits, you're then going to have to slow it down. So then slow down. Again, to whatever speed is required, you could calculate that. G, M, E, and we can call this R3. We can call that R1, and we can call that R3. If you don't slow it down, you won't have a circular orbit. You'll end up with a little bit more of an elliptical orbit. In order to have a circular orbit at that location, it has to be that specific speed. All right, I'm going to call it a day. We're going to stop here. Hopefully this you could follow. Definitely give me advice on how this goes. If you want me to be quicker, if you want me to be slower, if you have suggestions, I'd love to hear it. And we got this. Yay, gravitation. Okay, ending. How do I end? Stop. All right, bye.